Okay, today we're going to talk about a new type of ADT called graphs. And what does it enable for us? Enables arbitrary relationships between data and unlike the tree, which was hierarchical, where we had to start from the root and go to any node, or like the list, where our access was always from the header node, or the queue, where you could only access the front or the rear, a stack, where you could only access the top, hash tables, where you really had no relationship between data items. The objective of a graph is to enable to start from anywhere, start from any node. We already saw, whether it's a list or a graph, is list or a tree or a stack or a queue. It's made up of a list of nodes. The objective is to start from any node and try to reach any node if there is a path. If there is a path. Okay. For example, I know that most of you must be using Google Maps. This imminently uses graphs. You may want to find the shortest path. And it's very nice that Google actually gives you multiple paths, but it will tell you. I mean, today Google is so good that it will tell you which paths are congested, which paths are not. And so on, right? And other applications, for example, you're registering for a course. There's prereqs, like this course, for example, 1200 was prereq. Unfortunately, this is not implemented in Seat. We would ideally like to avoid heartburn that course allocation checks requisites. Okay. Then what you're doing is you're doing something like a topological sort. Okay, we'll see what all these are. And why is it a graph again? I mean, remember, graph is about any node connecting to any other node. Why is it again a graph? Because different students have different interests in different courses from one to the, and whatever courses you take, so each person will have a separate topological sort, which will tell you what are your prereqs that you have to satisfy. Other kind is the match the following. You might have done this in school. You have A, B, C, D, A, B, C, D, E, and the objective is to map from X to Y. But notice that there are no paths between elements in X or elements in Y. So no paths from within X, within elements of X, or rather between elements of X, of X are between elements of Y. Okay. We only have paths across, only paths across. Such a graph is called a bipartite graph. Okay. See more about this later. Sometimes, you want to, let us say, you take the roadways in Chennai. And you want information, some information, or even let's say, let's not talk about roadways. Let's say I have a network of um, cell phone towers. Now the government wants to um, send some information, breaking news, for example, as quickly as possible. Possible. Then what you do is you want to find a tree in the graph because you don't want to go through multiple paths. Graph and a broadcast tree. Okay, this could be something like what's called a minimum spanning tree. There's a lot of use for all of this. Okay, tree, how quickly can I reach all the nodes in a graph? And there are other applications. We do have traversal of graphs, just like we have traversal of trees. And there are two typical traversals: breadth first, as wide as possible, and as deep as possible. Okay. So I've generally given you some vague idea that there are a set of nodes which are arbitrarily connected. And now let's look at a little more carefully. What is actually a graph? There are two types of graphs. Directed and undirected. Okay. Let's see what is a directed graph. So graph is also made up of nodes and it has edges or arcs like this. Okay. When the edges are directed, we call it a directed graph. When the edges are not directed, we call it an undirected graph. We'll see what is the meaning of this, okay, in a little while. Like this, okay. Let's see, we have a graph like this. I call this a directed graph. Why is it directed? It says there is a path from, what does this mean here? It says there's a path from 1 to 2, but there's no path from 2 to 1. An undirected graph, on the other hand, will look something like this. Same one if it was undirected. Four. This is an undirected graph. Whenever we draw a graph without direction on the edges, this means this is bidirectional. Generally, that is the meaning of it. Bidirectional graph. Okay. So by now, with all these examples, If it's a directed graph, we have a path from a vertex V to a vertex W. So clearly, what is a graph made up of? Vertices and edges. So vertices are like your elements that we have looked at in various other data structures. These are the vertices. And these are the edges. What do these edges tell us? The relationship between the vertices. Some relationship that's there. Okay? It could be cities and roads or whatever. Okay? And one important point that it tells us is when I have a directed graph and I say V2W is an edge, this means W is adjacent to V. Okay. Vertices and edges, as we said. Examples: vertices can be cities, and edges can be flights between cities, which connect the two cities, between cities. Okay. Can also have a computer program represented by a graph. So I have a start node, start of the program, then let's say I check some condition. So this is one node, node 1, node 2, and depending upon the condition, yes, no, I might do something else. 3, 4, and end perhaps. So if you look at this in the computer program, to reach the end, I have two different paths. I can take either this path or I can take this path. Okay. So what we do is we generally represent a path as in a directed graph, which is also called a digraph. A path in a directed graph also called a digraph is a sequence of vertices. Okay. V1, V2, Vn implies there is a path V1 to V2, V2 to V3, and so on, and from Vn minus 1 to Vn. This also tells us that V2 is adjacent to V1, V3 is adjacent to V2, Vn is adjacent to Vn minus 1. What is the path length? This example is n minus 1. This is similar to a tree, okay, where you have the length of the path from the root to the leaf node is the height. Then a path can be simple. If all vertices on the path except possibly the first and the last node. This is an interesting example. First and the last are distinct. So that means what? I can have a path which starts from a particular node, goes like this, and comes back. This is a path. Okay. So this forms what is called a simple cycle. A simple cycle is a path of length at least 1, starts and ends at the same vertex. Okay, so let's go back to this example of the graph with vertices and here, for example, I have a nice 3, 2, 4, and 3. Is a simple cycle. Okay. So this was 3, 2, 4, 3 in the example that we saw of a digraph. Sometimes, or sometimes, many applications actually. Many applications associate or attach additional labels to the vertices and edges or arcs of a digraph. Then we call this a labeled diagram. Let's take an example. Okay, this is called a transition graph. You transit from one node to another, incurring a cost of 1 to 2, you incur a cost of A, and 2 to 1, you incur another cost of A. And it's interesting that transitioning from one to itself leads to a sequence of A's and B's that are whose number is always even. This is an interesting problem later you will see in graphs. Whose number is always even. Okay. Okay. So we'll take up the definition and representation of the ADT graph in a little while. Let me stop here.